So far, we are done with basic Python and the 4 important libraries that surround that. The NumPy, the Pandas, the Matplotlib, and the Seaborn. So what you may have to do is basically do some kind of a practice by picking up different kinds of data sets of your choice from Kaggle. So you actually get on to Kaggle, you pick up any data of your domain or of your choice and probably apply whatever we have typically discussed. Try to apply to that, right? So that you will get different perspectives. Now, when we are moving more towards, when we are calling something as data science, obviously now we will have to work with the data and we will have to typically do some kind of a manipulation on the data. So that is where generally what we say is, initially you start with the descriptives, right? You try to understand the data. Descriptives is nothing but you try to understand the data. You try to do a kind of inferential. In inferential, we talk about typically try to understand relationships in the data. So basically, this has something to do with what is called as feature selection. And then we talk about predictive analytics, where we talk about model building. And possibly data preparation. So these are the various stages that come into picture. Now, when you are trying to do an understanding of the data, obviously the understanding can happen through 2 major routes. One is some kind of summarization of the data. 2 is visualization of the data. When we are typically using the concept of understanding of the data, we understand it primarily through 2 routes. One is we do a kind of visualization, for which we have used Matplotlib and we used the Matplotlib and the Seaborn. So we were trying to understand what happened with the historical data, right? With the historical data, what had actually happened. So just trying to understand the primary, there are multiple things that we do when we understand it, but primarily some of the important outputs that we try to see is, are there any missing values in the data? Are there any erroneous entries in the data? Are there any insufficient data points? Are there any extreme observations in the data? Are there any variables that need to be omitted? So these are some of, and possibly there might be a couple of more things as well. So these are some of the major objectives that I would like to attain by doing the descriptive statistics. So I will not take any actions here, right? So the outcome of this is some action, but when I'm purely doing a kind of a descriptive statistics, I am simply trying to look at, are any of these things possible? And sometimes even I would like to understand what is the broad pattern of the data. So these are some of the things. Possibly we might get a few more insights, but these are some of the things that we would typically try to look at. Okay, is that still the problem? Hello. I'll put a backup with my hotspot as well. Okay, now I'll put one backup with hotspot so that if at all my primary network is down, hotspot can act as a backup. Okay. So we are first trying to understand to whatever extent possible, because if I have to build a good model, obviously I have to understand the data to the core. And once I understand the data, inferential is primarily about which data points, which variables will be useful and which variables will not be useful for building my model. Many a times what can very well happen is we might have collected so many variables for our model building exercise, but we may know that many of the variables, they do not contribute much to the target. So in that case, better knock out those variables. So inferential is actually an intermediate step before I jump into prediction. Possibly I can use some kind of statistical tests. I can use some kind of statistical tests to typically infer whether this variable will be having an influence on my target, or this particular variable can be totally ignored. Sometimes people skip this step also, but what we generally understand is this step will be a very, very essential step. So what we generally say is you start off with the descriptives. Right? Then, so try to find out if there are any missing values, if there are erroneous entries. So what we say, once the stage is done, do the necessary correction. So your data which seems to be erroneous here, or some error values, we are trying to do the necessary corrections to the data. And once we do that, you try to see which variables are good to retain and which are worth discarding. So you can use various methods to do that, right? Inferential statistics is one of the ways, but we can very well think about a broader name called feature selection. Right? Feature selection can happen through various approaches. So we are talking about some of those here. Then you jump on to the predictive. Now you have your models in place, then you jump on to the predictive. That is what will actually be the process of building different kinds of statistical models and machine learning models on the data. All right. So we will spend some time in terms of doing, we have already done visualization. Based on the visualizations, we could typically see something with the data. Now, we would try to see the basic descriptive statistics. I think most of you would be comfortable with that aspect, right? But we are quickly looking at some of the aspects out of them today. So this is going to be a slightly lighter exercise. I don't want to spend much time on it, but definitely when we are actually taking up one good data set for an end-to-end, this is the data set which we can still go ahead for our end-to-end exercise. And so here I would be taking the two data sets. One is anyhow we have taken the lone default data set. So this is one data set we would be actually using for a kind of problems classification problems. I'll define these problems slightly later. And we would also be using another data set called medical expenses data set, which could be for something like a regression problem. So these are the two data sets that we would be using, right? And possibly you can very well go ahead selecting your own data sets from your own domain for the process of end-to-end predictions model as such. So right now it's a very simpler topic, right? I think most of you might be knowing about all these things. So once I take this, I'll just go through these, and towards the end, I'll use one mega function which can calculate a lot of things about our data. And by looking at that, you should be in a position to understand the data in totality. Okay, so these are the basic calculations that we do on any data that we get. So we are simply connecting to our data. So it is there in my Google Drive. So I am connecting to my Google Drive and I am loading the lone default data. I'm loading the lone default data using the pandas read CSV kind of a command, and possibly looking at the first few observations. Okay, so you could we could see that there are so many categorical variables, there are so many numerical variables in the data. Okay, so this is what is the data that we have been using also. So I can very well look at the shape of the data to typically find out how many rows and how many columns are there in the data. So I have been given a kind of a data set to explore. So I am looking at a lot of variables. So I need to understand the entire data before I I go ahead in terms of doing the predictive model on the top of it. So I know that the target is better predictability of the status. That is the target or the objective of this exercise. So how well I can relate status with all the other values that I have. So how many of these variables they can explain the status better? They are very much. So which of these variables are related to the status? Which of these variables are not related to the status? That is something that we may have to work out as well. So that is where we are saying we will try to do feature selection or trying to understand the relationship between the variables. I'm really sorry, I don't know what is happening. My signal is looking pretty much full. There is nothing much that I think I can do. If it is becoming too much of a problem, then I don't know, we may have to reschedule the session. Because I have no clue on why it is going slow. Okay. So once you take the data, the objective always, this is for any kind of analysis that you want to do, right? This is for any kind of analysis that you want to do. The moment you are given a data, try to understand the data as much as possible. So understanding is as good as right from the basics. You look at the head, tail kind of things. You look at the shape of the data, right? If required, you can very well find out possibly or probably I'll knock out all these activities here, right? Possibly we'll directly get on to the full-fledged summary. I don't think we require all these things. I'm knocking them out. Yeah, I think this one instance would be more than sufficient. More than that, possibly we have used a few functions earlier, right? We have used a few functions like info. I'm sure all of you are comfortable with the usage of info, which will tell you how many null values and all are there in the data, and what is the data type of each of the set of values. Now, I think the most important thing that you can look at here is the descriptive statistics. You are trying to describe the data, right? You are trying to describe the data. Now, I think this particular element will give you many insights. This particular function will give you altogether all kinds of insights into the data. So you are simply taking there is in the stat models, there is a kind of a module called descriptive stats, and we are trying to import a function called describe from the descriptive stats. This describe, actually, you see there are so many calculations that it does. And the describe typically works with numerical data by default. Right? The describe actually works with numerical data by default. Right? So you could very well see that it has actually given the kind of calculations for a lot of numerical variables. So you could see that these are the various stats that it typically gives, right? Number of observers. We'll discuss each one of them. Whether to include categorical columns in the descriptive statistics, whether to include numerical columns in the descriptive statistics. So there are so many other things that are being mentioned, whether to include some of them or not to include some of them. Okay. So we will move ahead with trying to understand in detail all these calculations. So we have seen that these are the various calculations that are typically done. So let us understand what are all the things that you really understand. First of all, ID. ID is a numerical column in our current data. Probably I may not be interested in having the ID as my data, right? Because ID is just a serial order, serial number. That serial number may not be playing a big role in the analysis aspect. So I may be more interested in dropping that ID as a column. So that is one observation that I get. And all these calculations that happen on the ID are really useless. Probably I may not be interested in having the ID as my data, right? Because ID is just a serial order, serial number. That serial number may not be playing a big role in the analysis aspect. So I may be more interested in dropping that ID as a column. So that is one observation that I get. And all these calculations that happen on the ID are really useless. Because ID is just a serial number. Probably number of observations is fine, but the mean value, the standard error, the upper confidence level, all these, they don't make sense at all, because ID is not a column which is typically worth including, right? Any ID does not make any sense unless you want to pinpoint to a particular ID that the value is very high for this ID, or so it's only from an indication perspective. It will never play a role in the model building aspect. So that is one thing that I think all of us need to be clear on. Anywhere we have the ID variable in our model, it typically does not make any kind of sense to include that in our model. Okay. So you can, when we are dropping, we can very well think of dropping that particular variable. But first we will see, and then we will take care of the dropping aspects. Similarly, here, in this problem, if I see, so now let's see what are all the observations. Number of observations is 1,48,670, no problem. No missing observation, fine. So for this column, no missing observation. Mean is 2019, so we all know. Standard error is 0. Standard error is 0 means there is no variation in the data at all. Right? Standard error is typically coming from sigma by root n. Standard deviation by square root of n. So you are clearly seeing that the standard error is 0 and the standard deviation is also 0. Which means there is no variation at all in the data. All the data points are 2019 only. And the moment I see that all the data points, all the 1,48,670 data points, they are all 2019 only. If that is the case, then obviously that particular column will not add any value to our analysis. That is one thing that we have to remember. Any column that has only one unique value, right? It does not have any kind of a standard deviation in it. No variability at all in that data. So that column is typically called as a zero variance column. And it is clearly suggested that zero variance column should be eliminated from our data. Otherwise, they create some other problems when we are doing the modeling. So as a part of the pre-processing aspects, we will remove one, the ID related columns, two, those columns which are more and more, having only one observation, one unique observation for the entire column. So here it might so happen that the year also will get knocked out. Now let's see the third one. So yeah, third one, the loan amount. Number of observations are fine. No missing observation in case of loan amount. The mean value is something. The standard error is this much. Now, the standard error is actually something that is helping you more in the inferential statistics. Not here, right? Standard error, upper confidence interval and lower confidence interval, they actually play a role in the inferential statistics. So generally, in the inferential statistics, we'll be seeing later that we always talk about a scenario whether the mean value of any variable, is significantly different from 0 or not. So that is what is the kind of question that we try to address, right? And here, this confidence interval typically talks about that. So basically, if I have a standard error, which generally comes out as standard deviation by the square root of the sample size, what is typically said is the 95% confidence interval for the mean is whatever is the mean that your system is saying, your computation has done the sample mean, plus or minus 1.96 times the standard error is what will be your confidence interval for the mean, 95% confidence interval for the mean. So in our case, the mean is 3,31,117. 3,31,117 plus or minus 1.96, probably let me round it up to 2, times the standard error is 1.23. So what is going to happen here? 1.237 is your standard error. So basically what could very well happen is So you could typically add and subtract to it, and that is what will give me your lower confidence interval and your upper confidence interval. So I have to actually go for 5 decimals. So it is actually 3,31,120. Right? The actual value is 3,31,177. And the lower upper confidence interval and lower confidence interval typically are 3,31,153 to 3,31,202. So what is that we are saying? If that interval contains 0, if that interval contains 0, which means the lower confidence interval should be less than 0 and upper confidence interval should be greater than 0, then we say the mean of that particular variable is not significantly different from 0. Mean of that variable is not significantly different from 0. There are so many applications where we talk about being significantly away from 0 versus can be considered as 0. So especially in a lot of time series related applications, etc., that becomes even more useful. So here we are not much finding that. Possibly we are seeing that it is very much significant, right? So don't bother. So this is the mean value. And we are saying this is the 95% confidence interval for the mean value. Then some of the other important, I think all of you know how to compute, or even if you don't know how to compute, does not matter. So the standard deviation is the next one. So the standard deviation is coming out for loan amount. The standard deviation is coming out as 1.839 into 10 to the power of 5. So what we are saying, this is the kind of average deviation of the observations from the mean value. So typically also it is computed as you are simply subtracting the observation from the mean, you are squaring it, you are summing it, you are dividing it by the total, which means you are taking the mean, which will make it as the variance. You put a square root under that, that is what will become the standard deviation. So, but an interpretation perspective, we are simply talking about that is the average deviation of the observation. Right? Now here, if the deviation is too high compared to the mean, sometimes we may even observe that some kind of extreme values or outlier values also could be present in the data. So standard deviation has to be looked at it from a relative perspective only. So generally what people do is the standard deviation divided by the mean is otherwise called coefficient of variance. Right? Sometimes the exercise that is typically done is with the original data, I find out what is the coefficient of variance. Let's say I have identified something as an outlier. I remove that outlier from the data and I recompute the coefficient of variance. Now, if I see that the coefficient of variance has changed drastically, has fallen drastically because of the removal of this one outlier, then it means that that outlier is a very significant outlier. Removal of that outlier will be a good thing, because the variation in the data has fallen quite drastically, right? So definitely too much of variation, if it is there in the data, obviously fitting of a model may not address all the requirements of that data. So if you are saying the data is widely varying, if it is not varying also, it's a big problem. If it is very widely varying also, it might not be possible that one single model capture all that variation. So that is where sometimes what we suggest is, if at all this ratio is going too high because of one observation or because of few observations, then it is a kind of an indicator that dropping those observations, if it brings down the coefficient of variance, then it is going to be a kind of an advantageous thing only. Then you look at this interquartile range. Interquartile range is typically coming out as the third quartile observation minus the first quartile observation. So the third quartile is nothing but the 75th percentile of the data. And the first quartile is nothing but the 25th percentile of the data. So you could see that between these two is the middle 50% of the data. So when I say interquartile range, I'm talking about the range of the middle 50% of the data. And similarly, if I look at the value called range, I have another value called range here. So you could see here the range is maximum minus minimum. So for the entire 100% of the data, for the entire 100% of the data, the range is 3.56 into 10 to the power of 6. And for the mid 50% of the data, the range is interquartile range, which is 2.4 into 10 to the power of 5. Normally, we are seeing, if I take the ratio of this, generally, this is a kind of an observation. If this ratio is generally greater than 3 or 4, right? 4 on the worst case. If this ratio is more than 4, I can very well sense some kind of extreme values being present in the data. The data can definitely have, because this is just a middle 50%. So even if I assume that the same range will lie towards the left and towards the right also, possibly we can still go up to 3 or something. The total cannot go beyond 3. But if the moment we are seeing the ratio to go much beyond 3 or 4, then it's a great scenario that then it's a great possibility that we can have a lot of extreme values in our data. So even if I do a kind of a rough check, it looks like this ratio is around 15. A quick calculation, this ratio could be somewhere around 15. So I can very well sense that there could be some extreme values being present in the data. Right? So that is how we are understanding the IQR, interquartile range. So then the other thing that we may be looking at, not necessarily, if at all the data follows a normal distribution. Here, in all these exercises, the normal distribution is a very essential element. In your modeling world, normal distribution, typically you might all be aware that it is a kind of a bell-shaped curve, right? So this distribution is a very, very essential distribution because a lot of models that you would be talking of, at least some of the statistical models, they make a clear assumption that your data is normally distributed. Right? Possibly if you are aware of the assumptions of a linear regression, you would clearly see one of the assumptions is the error terms are normally distributed. And the second assumption that you will find is there is a linear association between, we will discuss them in detail, linear association between X and Y. Now, if I combine these two assumptions together, I would typically say that the linear regression can typically model the relationship between X and Y if X and Y are normally distributed. Right? If X and Y are normally distributed, then the relationship can be measured very appropriately. Okay? Mean of error is 0. Okay? Which is very much true in a linear regression exercise. Mean of error is always a 0. Okay, my intention is something. So what I'm trying to say is the importance of normal distribution. So there are so many cases where you typically expect a particular data to be normally distributed. So in the whole process, we would very well be interested in checking whether how many variables are normally distributed and how many of them are well deviating from normal. So that is the reason why all these descriptive statistics also, they give that kind of a value. So if at all this data would have been a normally distributed data, the IQR, the interquartile range, would have been 1.77 into 10 to the power of 5. So we could clearly see that the actual IQR, so here these guys, the value, the way these values are typically computed is based on a kind of a simulation exercise by using the parameters of the same distribution. Parameters of the data under the assumption of a normal distribution, simulate the data, and based on that you compute the IQR. So it looks like the interquartile range under a normal distribution assumption is only 1.77 into 10 to the power of 5. So it looks like at least the actual IQR is almost 50% or at least 30-40% more than the IQR if it would have been a kind of a normal distribution. So that is also one pointer that is telling you that this particular data point would not have been a kind of a normal distribution. Then the next measure that we are looking at is the mean absolute deviation. Mean absolute deviation is talking about the same as the standard deviation, but typically instead of taking the squaring, it is taking the absolute value. Instead of squaring and then square rooting, it will take the absolute. So this is also another measure of average deviation from the mean. Of course, out of all these measures of average deviation from the mean, we generally consider standard deviation as a better measure. So this is just to understand. But again, in this case also you could see for a normal if the data would have been normally distributed, this would have been the mean absolute deviation. But again, here also we are seeing the mean absolute deviation to be more or less deviating from that of the actual one is deviating from the assumption of a normal distribution. And we have already talked about the coefficient of variance, which is nothing but the standard deviation 1.83 into 10 to the power of 5 divided by the mean 3.31 into 10 to the power of 5. So the ratio is somewhere around 0.55. So what we say is, if at all I have identified something as an outlier in this data, and I eliminate that outlier from the data, then we simply say that this coefficient of variance should come down quite drastically. The moment it comes down quite drastically, then possibly that one or few observations that we deleted, they are really significant observation, really impacting observation. So we have the maximum value, we have the minimum value, right? We also have the median value. We all know how to calculate all these. The mode actually ignore it. Mode in case of continuous data, the mode really does not make much sense. So it is just computed, but possibly you can ignore the mode. Mode and mode frequency, you can ignore it because it is especially useful when you are talking about categorical data. But in case of continuous data, it does not make much sense. So you can very well ignore the mode. Then come two calculations, skewness and cutoffs. These are the two important calculations that actually drive normality of the data. So these two, they typically drive whether your data is more normally distributed or not. So what is that we are saying here? The coefficient of skewness is again the same calculation. Observation from the mean, instead of squaring or instead of absolute, take the cubic, right? And take the average. So this is what will be coming out as skewness. Whereas to make it more uniform and comparable, there is a coefficient of skewness that is created, which is typically taken as skewness divided by the standard deviation to the power 3/2, standard deviation whole cube. So this is what is taken as the coefficient of skewness. It can be negative or positive. Obviously, if the value is 0, what we say is the data is more symmetric. If the skewness coefficient is 0, we call that the data is symmetric. If the value is negative, we say that the data is more left skewed. Left skewed means you will, when you plot a kind of a histogram, you will get something like this. So your majority of the values, your peak of values will be lying towards this side, but you will have a few values in the extreme left side. So extremely low values are possible here compared to the rest, but major chunk of the observations would be concentrated towards the higher value. So these kind of scenarios, you will very well find the negative skewness. And one of the typical characteristics that you see in negative skewness is your mean should be much lesser than the median in this case. This is the characteristic what you see in a negatively skewed kind of a data. Now, why do we do that? Just wait for a few minutes. Similarly, if my data is having a positive skew, it would be more like this. A large chunk of values will be towards the lower side, but I will have a few values lying so big because in my histogram, they would be typically coming towards the extreme right with a smaller frequency. So this kind of a data is typically called as my right skewed or positively skewed kind of a data, where you generally observe that the mean is greater than the median. Now, why we talk about this kind of data again is to link it with a kind of normality. Generally, a symmetric data, right? I'm not equating these two. Generally, a symmetric data, normal data is symmetric, not necessarily the vice versa. The symmetric data need not be normal, but normal data will be symmetric. So, which means we were saying that the normality of the data is one of the very essential criteria for some of the important models to be executed. If I have to execute some of the most important machine learning models or even the statistical models, the normality of the data becomes one of the essential criteria for me. So here, if it is left skewed or right skewed, then possibly normality is slightly getting disturbed for that particular data. So we want to see how much the data is deviating from normality. Right? Skewness is one way which is saying from one dimension, how much it is deviating. So typically what is that we are saying in symmetric? On a large scale, if I am talking about something like a mean here, you can simply see the extreme value this side versus the extreme value this side. If they are more or less similar, then it looks like a kind of a symmetric. But otherwise, if I see that the mean value is here, the minimum is here, but the maximum is here, it's all probability you will see that there could be a kind of positive skewness in that kind of a data. So generally what happens is, because the data is not normal, while doing the pre-processing, we will see if I can do some transformations, if I can do some internal transformations, to transform the data closer to normal. If I can do some internal transformation to transform the data closer to normal, so that I can use many models more comfortably. So that is where what could very well happen is, depending on if the skewness is very positive, I would try to do some kind of transform which would bring down the range. So sometimes what we say, of course, we have the tools and we have the functions which can actually do this non-linear transformations. We are typically calling them as Box-Cox transform or Eo-Johnson transform. Right now, don't bother about them because we will use them as a part of our data pre-processing before we give input to the model. But now we are saying the importance of normality of the data is very, very essential. So from that standpoint, I could clearly see here the skewness for this particular variable loan amount is 1.66 into 10 to the power of 0. So it is around 1.66. So it is definitely not 0. It is positive. It is positive means it's a positively skewed value. You are right, Dev. Third and fourth central moments are skewness and kurtosis. Calculation is one aspect, but interpretation is what we are focusing on. So we say that the data is more skewed towards the right. Data is more skewed towards the right, so which means there is a possibility of some extreme values on the right side of the data. Towards the right side of the data, towards the higher side, positive side of the data. Then we are also talking of another variable, another measure called kurtosis. So as Dave has already highlighted, the way you compute this is the fourth moment. And similarly, the coefficient of kurtosis will become kurtosis value. You standardize it by taking the fourth power of the standard deviation. And what we say is, if the data is more normally distributed here, it will have a kurtosis of 3. So the kurtosis typically talks about the fatness of the tails. And it would also talk about the peakedness of the distribution. So basically, you look at it as a fatness of a tail. So if we typically talk about a normal distribution, right? So this is what we are calling as our tail. This is what we are calling as our tail. Now, when I'm saying, so the area in the tail is should be this much. The area of the tail is something this much. So now, when I'm saying a fat tail, so the extreme values are much more extreme the extreme values are much more extreme. So what is that we are seeing? The tail is appearing much fatter here. The tail is appearing much fatter, right? Compared to the normal distribution. Here the comparison is with respect to normal distribution. The tail is much fatter with respect to normal distribution if the kurtosis is greater than 3. And if the kurtosis is less than 3, then we say tail is thinner. Tail is thinner with respect to the normal distribution. So overall, it is deviating from the normal distribution, whether it is thinner or fatter, but overall, it is deviating from the normal distribution. So both skewness and kurtosis, possibly for a And in some case, some softwares or some function, this kurtosis is actually measured as something called excess kurtosis, which is nothing but kurtosis minus 3. So a simple 3 is subtracted just to say that for a normal distribution, the excess kurtosis will be 0. So if it is greater than 0, then we say that the tails are fatter, and that scenario is typically called as leptokurtic data. And similarly, if the excess kurtosis is less than 0, because kurtosis less than 3 is nothing but excess kurtosis less than 0. So if the excess kurtosis is less than 0, we typically call it as a platykurtic kind of a data. And it typically is having a thinner tails compared to that of a normal. Anyway, both of them are deviating from the normal. So both of them taken together, the skewness and the kurtosis, both of them taken together, there is one test called Jark-Bera test. There is one statistical test called Jark-Bera test, which simply takes skewness and the kurtosis values, and based on this gives a kind of a conclusion or inference, inference. Possibly we'll talk about the meaning of inferences and all in the next topic. But because it has done some calculations here and we are discussing now. So it gives an inference whether your data is normally distributed or not. So simple way right now, how you can say whether the data is normally distributed or not is simply don't look at the Jark-Bera value, look at the Jark-Bera p-value. Right now we are not discussing about the inferences and all. We are simply saying just look at the Jark-Bera p-value. If the p-value is less than 0.05, then you say the data is not normal. That particular data is not normal statistically. So this test is done by using both the skewness and the kurtosis value. So if the p-value is shown as less than 0.05, then you are concluding that the data is statistically not normal. Possibly if it is greater than 0.05, you don't have the necessary evidence to say that it is not normal. So you would typically be considering that the data is almost close to normal. So that is what we typically see as a part of the descriptive statistics. So these are some of the things. And we could clearly see that most of our variables, they are not normal. You see here, the skewness is 0.38. The kurtosis is 3.34. Both are looking positive. And your Jark-Bera value is still a 0, which is saying p-value is 0, saying it is still not a normal distribution. Similarly, the skewness is 0.28. The kurtosis is 2.81. Still the p-value is 0. So we are seeing here, in some cases, the skewness and kurtosis are absolutely higher. And in some cases, they are pretty much closer to 3 for the kurtosis and pretty much closer to 0 for the skewness. But still, in this big data size, when the data sizes are small, possibly these numbers would have been still considered to be close to normal. But because of a data size of 1,48,000 records, even the small deviations from 0 right? This is just 0.38 deviation from 0 and this is just 0.34 deviation from 3. Even these small deviations, they are so significant that the Jark-Bera test is getting rejected. The same logic here, you see, it's only 0.28 deviation from 0 and only 0.19 deviation from 0, from 3. So still we are seeing that the Jark-Bera test is simply saying the data is not normal. So with almost all the data points, we could see that the data is not normal. And at the same time, some of the important things that I also suggest to be understood here. Look at the minimum and the maximum. The other important analysis that you will have to do is look at the minimum and the maximum and see if there are any abnormal values. Like in some cases, the minimum is not acceptable or something. For example, this is the loan application, right? And in the rate of interest, I see that the minimum value is 0. Is it really possible? I don't want to comment on them, but this is something that we may have to explore in the data and try to bring out. The minimum value of 0, is it possible in the rate of interest to have a minimum value of 0? If it is not, then we have to highlight this and possibly try to do the handling of this, right? Similarly, look at the maximum. Is the maximum very much allowed or not? So always look at the minimums and the maximums of all the numerical columns. Now, when you are looking at the minimum and the maximums of the numerical column, sometimes it is pretty much clear that these are some erroneous kind of values, right? Possibly if I am saying that the rate of interest is 0, it is very much possibly when there were stages where the risk-free rates of some countries were negative, quantitative easing kind of a scenario, wherein we were discussing, so we are seeing whether the rate of interest at that time was typically 0. So someone might say in a Islamic banking or Islamic finance kind of a world, the interest rates are 0. So from that perspective, 0 might look like an accepted rate. But if it is a regular loans and all, I don't know whether 0 need to be accepted. So possibly we may have to dig through, and in case we find that 0 is very much possible, we'll have to simply ignore it. But if we come to know that 0 is not possible, then we may have to drop that particular variable or drop that particular observation. So that is how the minimums and the maximums are going to help me. Interest rate spread, it looks like from minus 3.63. So you are in some cases the customers are charged lesser than the risk-free rate. Might be possible because of some priority given to some customers. Maximum spread is around 3.357. That should be fine. But the next upfront charges are from 0 to 60,000. Okay, some customers you did not charge anything extra. Might be possible. Then the term of the loan ranging from 96 years, which is 96 months, which is 8 years, to 360 months, which is almost like 30 years. So very much possible, 30-year loan. Then we are talking about property value ranging from only 8,000. So a very small property, 8,000 to almost it is going for a 1.65 crore. So possibly, I mean, I'm imagining now the intention is sit with the business expert, sit with the domain expert, feasible or not. Then similarly, I am seeing 10 here. Income. The income of the person is 0. Now I don't know. It might very well be possible. I have lost the job, right? The person who, at the time of application of the loan, he or she might have lost the job. So in that particular period, the income might look like a zero. So we can't completely discard it. But based on the discussion, or possibly in this case, we'll make these kind of assumptions. We'll say that the income cannot be zero. So we will try to treat these kind of records as some kind of abnormal value, erroneous value. And just that we want to handle something. So that's the reason I wanted to consider that scenario. Then possibly credit score is lying between 500 to 900. Loan to value ratio is lying between 0.96 to almost 7,800. So looks like there are some cases where compared to the value of the property, the loan given has been significantly higher. We don't know whether those kind of loans are typically defaulting to a large extent or not. And then we have a status which is just a 1 or a 0. So the minimum is 0, maximum is 1. And finally, we have the debt to income ratio. Debt to income ratio is ranging from 5 times the income has been taken in the form of debt to 61 times the income has been taken in the form of debt. So we don't know, possibly people who have taken a larger debt to income ratio, is it like those people have defaulted more compared to the other set of people? So this is where you could see for all the numerical variables, this kind of analysis is typically this kind of summarization. There's no analysis, but by dwelling more and more into the data, you will get more insights into it, and accordingly you can do some kind of pre-processing in a better way before you actually get into the building of the model. That is what is the intention behind this exercise. Not the debt to income, it is debt, DEBT, debt. Debt to income, so which is the loan to income ratio. Yeah. So how much of loan you have taken for in proportion to the income that you have. So your salary versus the loan that you have taken. Okay. So the intention is try picking up any such kind of data sets, and corresponding to that data set, look at the descriptive statistics and try to understand those. So this is one thing, right, which as a part of the basic statistics. I'm just giving all the basics here, right? When we are doing a modeling, generally this is the flow that we go with. When we are going for any predictive approach, right, any data being given, we are typically working with the data, we are trying to analyze the data. These are some of the steps, right? Initially try to analyze the data, bring out some interesting patterns from the data. So this function is doing completely with respect to numerical columns only. But we also have some non-numerical columns are typically which are the categorical columns, right? Probably here I will put for I'll put for a categorical column. Now you see loan limit. Totally there are 145, 326. So which means we have a reduced number. So 148, 45, 326. So which means there are some missing values, right? There are some missing values for this column. And the other important thing that we will look at is how many unique values are there. As we have already discussed some time back, any column with just one unique value, it's better to drop that column because that column does not carry any information for you to build the model. So here there are two unique values, right? But at the same time, right, though there are two unique values, it might very well be possible out of, let's say, 1,48,670, 1,48,670, possibly 1,48,600 could be of one category and 70 could be of second category. So in these kind of cases also, possibly you can say each category should be at least, each category should be at least 50 elements. Each category should be at least 50 elements. Because if it is not the case, see, generally what happens is after a certain point, we will talk about splitting the data into training data, testing data. We build the model only on the training data. So if the number of observations of a particular category are very, very low, then that particular model, that particular variable would not contribute, that particular category would not contribute much to your understanding. So from that perspective, what is typically suggested is each category should have at least 50 elements. And if there is any category in a particular variable which is having much lesser than that, it's better to remove that category from the study. So removing a category, possibly when it comes, we will look at it. So 50 or 70, you can just check, especially in a very big data like this, possibly even 100 should be good enough. But yeah, so what we are seeing here, let us see if there is any such kind of a scenario, then we will discuss it. The loan limit, okay, there are only two categories. Some CF is the top occurring category with 1,35,000 observations. So possibly the other category is somewhere around 10,000 observations, but still that's okay. Then gender, 4 unique values are there. So we have to really check whether all 4 are valid or not. We'll discuss about those. We'll have to go deeper into it. So the male is the topmost category with 42,000 occurrences. Then approved loan in advance, there are some missing values. Only 2 unique observations, no pre-approved 1,24,000. So the other one could be more than that. More than 20,000 or something like that. Then loan type, 3 types are there, but one of them itself is 1,13,000. So we'll have to check the frequency of the other 2. If there is anything that is falling much lower, then we may have to act accordingly. Loan purpose, okay. 4 unique values are there. Credit worthiness. So here only 2 categories, but one of them is 1,42,000. So basically the other one is the remaining 6,000, which is still okay. Open credit, look at this. There are only 2 categories, right? And one of the categories is 1,48,114. So the other one is somewhere around 500 observations. 500 may still be okay, right? To do the model, 500 may still be okay. Now, business or commercial, again, only two categories. 127 looks pretty much fine. Negative amortization, some missing values are there. Not negative, 133,000. So possibly 15,000 are the negative amortization. Interest rate only, again, not interest rate only. We are having 141 observation, 1,41,000. So typically around 7,000 is interest only kind of things. Lump sum payment, again the same, only two categories. 1,45,000 are not lump sum, so which means still 3,000 are falling under the lump sum, which is pretty much a fine number. Yeah, look at this one. Construction type. Totally 1,48,670 records. The maximum, only two categories. The maximum occurring category is SB, whatever it is. It is having 1,48,637 records. So looks like only 33 records are in the other category. Only 33 observations are there in the other category. If it is only 33 observations, then it is better because it may not give any kind of a mileage to you. So it would be better to either, so there are two ways here. One, if you say, no, this variable is a very important variable for me because theoretically I know that the construction type plays a very important role in terms of finding whether the person will default or not. So in that kind of a case, better try to collect some more data so that you can still go ahead using the construction type. Or we have another mechanism like we can do some kind of oversampling, but definitely we don't suggest such kind of oversamplings or undersamplings with the variables, with the features. We generally look at from the perspective of the target and try to do this oversampling and undersampling. But here, so it might be very much possible that I may have to drop this category. But if I drop this category, the second category, whatever it is there, if I drop that category, what will typically happen is only one unique category will be there. So which means that column itself may have to be dropped. So construction type column itself may have to be dropped because if I drop that category, it becomes only unique category. Unique category, one unique category, and we have already discussed that one unique category is better to be dropped. Then similarly, we are seeing the occupancy type is fine, 1,38,000, but there are three categories. So we have to see the frequencies of the remaining two categories. If any of them is falling lesser than 100 or 50 something. Secured by is also having the same problem like your construction type. I think 33. So secured by home is 1,48,637, whereas the other one is still 33. We don't know what is the other one, but that other one is typically falling under 33. So that's also something which might go for a problem. Then similarly, total units, there are 4 categories altogether, but out of them, 1 unit category we are seeing around 1,46,480. So the remaining 3 categories you typically see only around 2,000. So we may have to see individually each count. We'll do that exercise. Right, credit type, again 4 categories with 48,000 for the CIB. Co-application credit is looking pretty much fine, only 2 categories, but 74,000 for one of them. Age is showing 7 categories, at least the major category is somewhere around this. Right, sometimes, okay, I'll also tell you there is one more criteria that we talk about. the highest frequency to the next highest frequency. Right? We set some kind of a number here. The highest to the next highest. Possibly it's as good as saying if I am setting 99% in case of two categories. So it is like I am setting 99 by 1. So then what is happening? 99 is the frequency of the highest category. 1 is the frequency of the next highest category. So if at all I am seeing that this ratio is, let's say, more than 1, then also we may directly say that those kind of columns can very well be removed, because are those kind of category, that category could be a influencing category altogether. So even in those cases also, it's better to remove a variable. You can even remove the variable also, because that variable is very much dominated by one value only compared to the other value. So in that case, we call them as near zero variance. So they are not zero variances, but they are very close to zero kind of variance. So it might very well be possible that we may end up dropping those kind of variables also. So right now we are only doing that kind of observatory stuff, right? Then the submission to the application is fine. The region, 4 regions are there. And security type also we have the same problem, right? Probably looks like 1,48,637, which means 33 observations are typically going for a toss. Only 33 are falling into the separate other category. And it might very well be possible. So right now, just by looking at the descriptive statistics, these are some of the initial understanding of the data that we have got. Yeah, we will check the remaining categories. I think we have all the mechanisms to check. By looking at the construction type and ratio of income to loan, the loan data consists of households and builders. I did not get your point. Construction type, okay, it's a home. And the ratio of income to loan, the loans data consists of households and builders. What does that mean? Okay. Then one more thing that you can very well look at is, we can go with a kind of we can take all these numerical columns. Okay. Let me just take all the numerical columns. Just give me a minute. We have to look at the next thing that you can look at now is, you can actually see some of the names of the columns. You can very well see the names of the columns. And if you want to rename those columns, you can use the command of rename. And you can very well give some kind of a what you call the dictionary kind of a notation, key value pair kind of a notation. Now, the other important thing that I wanted to talk about here is, let's say I want to typically drive, right? Possibly I want to talk about the numerical columns and the categorical column. So I would typically say the categorical columns here. So if you really want to print them, you want to print the categorical because you want to handle them separately. So I am taking the categorical columns and let's say I am taking the numerical column. So the loan limit, gender, they are all categorical columns. ID, year, loan amount, etc. are all numerical columns. Now, typically, it might very well be possible that the data correlation is more and more applicable only to numerical column. So you might very well see here, this is the biggest problem. If the year is there, and if for the year there is only one value altogether, and if there is only one value and the variability is not there in the data, then what you will typically observe is the correlation with all the variables will be undefined. And that is also one more reason we would very well drop any such kind of a variable. So correlation is actually telling you which variables are highly correlated and which variables are not that highly correlated, which are positively related to each other, which are negatively related to each other. Because this is one exercise that can really help us in shortlisting which variables to be retained and which variables to be knocked off. So we will talk about various such kind of mechanisms, right? But here we are just trying to do a kind of a quick descriptive statistics of the process. So possibly you can see which of them are very highly positive. So here I could see some kind of highly decently negative kind of a number. Debt to income ratio versus income, slightly a negative relationship is there, right? I'm not able to see some big numbers are typically not possible. So here there is some which may be significant. Debt to income ratio vis-a-vis the LTV, loan to value ratio. And like, oh, this is something. So there is a good correlation between property value and the loan amount, right? Obviously, if the value of the property is higher, the loan amount could be higher and vice versa. So sometimes in a numerical format, or you can very well take it into a kind of a graphical format as well. So we have seen the, so possibly you can even play out with the figure size. So you can go for a bigger figure and possibly you can plot a kind of correlation plot also in the form of a heat map. So I think that should be fine. We have already covered them. So that is what it is. I think we have, to a large extent, we have captured the descriptive statistics, which is one of the essential elements before you actually get into a model building process. So what I request all of you is take up some other data as well, right? Whatever the data that you are interested in, you take up another data set and probably try to run the descriptive. Running is always the simpler thing, but what all kinds of understanding you bring out of it. In the next class, we will actually handle all those we have identified. Probably we have identified some missing values. We have identified some zeros which we thought that they may not be worth enough in the model, or we are seeing some kind of extreme values which we want to delete. So all whatever we have identified, right, we will try to handle them and then take the things forward in the next class, from the next class onwards. I have been sharing whatever we are creating, but yeah, possibly let me share it. I have shared with Ravindra and asked them to share because some people are finding it difficult when I'm sharing it on the WhatsApp because some people are not there on WhatsApp or something like that. So that's where I sent him in an email to and asked them to share the email with all of you. Probably I'll ask him to do it today also. Can you please give the data? If the data is same, we can discuss in the class. Yeah, data I think I have shared if I'm not wrong. And in case I have not shared, I'll share the data as well. So I'll share all three, possibly the today's class. They're all there in my Google whatever drive. So I'll share those things. So from the next class onward, there would be a lot of activities that happen on the data itself, possibly linking more and more closer, moving more and more closer towards the analysis aspect. But of course, some kind of topics we would be keeping on discussing a little bit of conceptual also because whenever we are doing machine learning or something, a little bit of understanding of the model is also very much required. So right from the linear regression, I would be spending some time to explain the background behind the model, right? So that possibly it could be a revision to someone who already knew it, but at least for others, it could be so someone who is really getting into the data science. So obviously, it could be a kind of a quick refresher, or sometimes it could clarify some of the concepts as well. All right. So I'll share with you the module 5, module 6 and the data set. Data set is a little bit huge, but yeah, you can, when you are practicing it, practice it with a slightly smaller data set, especially if your system configuration requirements are slightly problematic. Anyhow, while building the model, I'll always do it with a smaller data set because within the class, I want the results to be much faster. So running on huge data sets obviously is going to consume a lot of time. All right. So I'll stop the session early today, a little bit, I think 10-15 minutes early. So in the meanwhile, I'll share these files as well, and possibly we'll work out in the next class as such. I think that should be fine. We have captured a lot of these things. So yeah. So if there are any questions, I'll discuss. Otherwise, we'll wind it up here for today. Thanks a lot, everyone, for listening to this session. See you on Wednesday. Thank you. Take care.